this problem, we're going to be looking at Newton's law of cooling, which is another separable differential equation. So Newton's law of cooling states that the rate of change of an object's temperature is proportional to the difference between its own temperature and the ambient temperature. If we let T sub t, or T of t, represent the temperature of an object as a function of time, then its derivative, dt over d little t, represents the rate at which that temperature changes, and the temperature of the object's surroundings can be represented by T sub s. So, what Newton's law of cooling basically says is this: that the change in temperature with respect to the change in time is equal to a proportionality constant, K, times the temperature of the object at any time t minus the temperature of its surroundings. Or, an easier way to kind of write this is just the change in temperature with respect to the change in time equals K times capital T minus T sub s. Now, the temperature of the object at the beginning of any experiment is going to be the initial value for our initial value problem. So temp at the beginning is considered to be initial temperature at t equals 0. So what we have is dt over d little t equals K times our temperature minus its surroundings. And the initial value conditions are capital T of 0 equals temperature at time 0, where K is a constant that is going to be given to us, or we're going to have to find it. So just remember that. That's our constant of proportionality. So I have a nice little problem here for us. It has to deal with my personal favorite food, and that's pizza. I absolutely love pizza. But anyways, let's go ahead and let's do this. A pizza is removed from the oven after baking thoroughly, and the temperature of the pizza when it comes out of the oven is 200 degrees Fahrenheit. The temperature of the kitchen is 75 degrees Fahrenheit, and after 1 minute, the temperature of the pizza is 190 degrees Fahrenheit. We would like to wait until the temperature of the pizza reaches 150 degrees Fahrenheit before cutting and serving it. How much longer will we have to wait? So all we really want to know is we're going to pull the pizza out of the oven. Newton's law of cooling says this is how long you're going to have to wait. So let's go ahead and let's start with our problem. So let's label some things we know. We know the ambient temperature is 75 degrees Fahrenheit. We also know the initial temperature is 200 degrees Fahrenheit. As soon as it comes out of the oven at T equals 0. All right. So Newton's law of cooling there we go. Newton's law of cooling turns into the change in temperature over the change in time is equal to K times T minus 75, where the initial conditions are T of 0 equals 200. So here is Newton's law of cooling. To solve this, we're going to go ahead and we're going to use our 5-step technique for solving separable equations that we're used to. So we're going to set the right-hand side to 0, or I'm sorry, setting the right-hand side of the equation equal to 0 gives t equals 75 as a constant solution. All right. Now, let's go ahead. So I guess this is step 1. Let me label that. Okay, step 2, we're going to rewrite the differential equation into its separable equation form. So we're going to divide both sides of the equation by t minus 75. And we're going to multiply both sides of the equation by dt. So we get dt over t minus 75 equals k times dt. Now, we're going to go ahead and integrate both sides. And by integrating both sides, we get the natural log of the absolute value of t minus 75 equals kt plus a constant. Step 4, we're going to go ahead and we're going to solve for t. So to solve for t, we're going to exponentiate both sides. On the left-hand side, we end up getting the natural log. We just end up getting the absolute value of t minus 75 equals e to the kt times e to the c. But what I'm going to do is I'm going to take this e to the c and rewrite it as c1. So we get the absolute value of t minus 75 equals c1 e to the kt. And since we know all these temperatures and everything are positive, we can go ahead and drop the absolute value to give us this. And finally, adding 75 to both sides of our equation yields t equals 75 plus c1 e to the kt. So this is our general solution. But this doesn't really tell us anything about how long do we have to wait. In order for us to figure that out, there are two things we need to solve for. We need to solve for c1, and then we need to solve for k. And that's really straightforward. So solving for c1, we're going to use the initial conditions. T of 0 equals 200. So our equation, which is what we just derived, turns into 200 equals 75 plus c1e to the k times 0. We know e to the k times 0 is e to the 0. So this whole thing goes to 1. So really, what we're left over with here is 200 equals 75 plus c1, which gives us c1 equal to 125. So far, we have t of t, which equals 75 plus 125 e to the kt. Now, the next thing we need to do is figure out what is k. Now, we've already used the initial conditions to find c, so we're going to need we need a little bit more information here. Luckily, we know that after 1 minute, our pizza temperature turned out to be 190 degrees. So we can use this to our advantage. So what we're going to do is we're going to say T of 1 equals 75 plus 125 e to the k times 1. But we know what T of 1 is. T of 1 is 190 degrees. So it's going to be 190 equals 75 plus 125 e to the k. Now all we have to do is just solve for k by first subtracting 75 from both sides. So 190 minus 75 is 115, which equals 125 e to the k. Now I'm going to divide both sides by 125 to give us 115 over 125 equals e to the k. And then to solve this, we're going to take the natural log of both sides of the equation. And by doing that, we can apply one of our properties for logs by pulling the exponent out front to give us the natural log of 115 over 125 is equal to k times the ln of e. By definition, the ln of e equals 1. So we just get k equals the natural log of 115 over 125. And I am doing this calculation on my calculator, but you can't see that. So I end up coming up with k is approximately negative 0.08338 rounded to 4 decimal places. So at the end of the day, here's what we have. Our differential equation turns into T of t, which equals 75 plus 125e to the negative 0.00838 to the t power. And this right here will tell us how long to wait for any desired temperature. Now, the problem said, how long are we going to have to wait for this to be 150 degrees? So what we want to know is, how long do we have to wait for the temperature to be 150? Well, that's really, really straightforward. All we have to do is just substitute in our temperature, which is 150, and that's going to equal 75 plus 125e to the negative 0.08338 t, and we just have to solve for t. So subtract 75 from both sides of the equation. That gives us 75 equals 125e to the negative 0.08338 t. Then we divide both sides by 125. So that's going to give us 75 over 125, e to the negative 0.08338 t. Once again, we're going to take the ln of both sides. So we get the ln of 75 over 125, which equals the natural log of e to the negative 0.08338 t. Apply our property for exponents dealing with logs. We know that's going to come out front. We also know the natural log of e is 1. So we just get the natural log of 75 over 125 equals negative 0.08338t. And then finally, we're going to divide both sides of our equation by that negative 0.08338. And when you do that, give me 1 second. I'm going to do it off camera. We get the natural log of 75 over 125 divided by, sorry, 8338. I end up with t equals 6.13, rounded to 2 decimal places, minutes. So all we have to do is wait 6 minutes, approximately, and you have a pizza that is at the perfect temperature of 150 degrees. I don't know if that's a perfect temperature to eat it. Seems a little hot, I don't know. But it would be a nice temperature to start cutting it, because you don't want the cheese to like instantly melt back together. You kind of want the cheese to stay cut. So I think that's a really good time to go ahead and cut it. I hope this made sense, and I'll see you in the next video.